In the last movie, we were discussing what happens this slide when we're using no datums, primary datum repeated in the feature-related tolerance zone framework, and then primary and secondary and what those mean. So no repeated datum features. There's no repeated datum features in the feature-relating tolerance zone framework. This would allow our holes to not be square to datum A. It's typically not used that way. What we would typically do is we would constrain those at least to datum A, and then that would square up our holes relative to datum A. So this would be the better way to do it. And the last one we were going to discuss was this one where we're using two datum references, the primary and the secondary um, datums are referenced in the pattern related tolerance zone framework. And what this does for us, first of all, it squares up our holes to datum A. We like that. And also it kind of makes it such that when we're specifying datum B as a secondary, what we're saying is we can shift these holes parallel to datum B. So we have some translation, but we don't allow any rotation about datum B. Um, in contrast, if we look at when just datum A, the primary datum, is referenced, what we're having here is when just the primary one is referenced, we can have some rotation with respect to datum B. But here, datum B is just strictly translation here. We don't allow any rotation with respect to datum B. Okay, so let's talk about multiple single segment feature control frames. This is a little bit different because the position tolerance symbol for both segments, it's a little bit different, and let's explain what that means. Okay, so here in the drawing we've got the upper, the pattern relating, the pattern locating, and the bottom we've got the feature relating. It's kind of like the same thing. So in the first one, it kind of works the exact same way. We've located our four holes with respect to datums A, B, and C. And then in this one here, what we've done is we're locating these same holes just back to A and B. And so what that does, it essentially squares us up. Our pattern location tolerance zone is constrained in translation and rotation to the reference datums. So that's what that one means. What is a functional gauge and functional gauging of positional tolerances? Okay, functional gauges can be used to inspect positional tolerances when the positional tolerance has an MMC modifier. So when the MMC modifier is used in a positional tolerance, we are open to use functional gauges to inspect the position of those parts, those holes, those features. So the gauge pins would be made to the virtual condition of the holes. That's for a hole, it's like an inside feature. The MMC would be the smallest hole minus the positional tolerance. That's how you would get to the virtual condition. And the part must fit over the pins and contact all three datum simulators. The fixed diameter pins on this functional gauge, they automatically permit bonus tolerances as the holes deviate from MMC. So as the holes deviate from MMC, they're going to fit this functional gauge even better. So that's what we're saying there. The fixed diameter pins at the virtual condition that are used in the functional gauge, those automatically give you an account for your bonus tolerances as the hole size deviates from MMC. Now, one thing about using functional gauges is that you need to verify the hole size separately, because the functional gauge will just check position of the holes. It will not check the size of the holes. Okay, so what does this mean? So here I've got a cartoon of a functional gauge made for a part. So this functional gauge will simulate the reference datum features and locate the virtual condition gauge pins relative to the datum reference frame. That tolerance zone framework is replicated within the functional gauge. And then to use this, okay, let's look at how this is done here. We have a simulator for each of the datums. In this case, it would be just a plate here, and then another plate here, and another plate here. And what this establishes is simulators for all three of our datum surfaces. A right here, B, which is along this surface, that's this big edge right here, and then C, which is along this surface right here, that's this edge right there. Okay, so this functional gauge has these 4 pins that are sunk into the datum A plate, and those pins are made to the virtual condition of the holes, which would be the smallest hole minus the tolerance at MMC. Okay, again, we got MMC, so that allows us to use this gauge. Okay, and so what we're saying here is the part must properly contact the datum features simulated with the gauge pins. Okay, so how do we check this part? We place the part in this functional gauge, and it has to fit over the 4 pins, and it has to contact datum A at least at 3 points, and it also has to be contact with datum B at least 2 points for a secondary datum, and it has to be in contact with datum C at least 1 point for the tertiary datum. So that is how a functional gauge works. It has features for the pins at MMC, and it has datum simulators for all 3 of the datums. And you put the part on there, and if you could touch all 3 of the datums and fit over all these holes, then you know that this part, these holes in this part, comply with the feature control frame that's specified right here. That is how a functional gauge works. Now keep this in mind, because this becomes the subject of your final project. Is drawing up a sketch of a functional gauge for me. And again, the hole size must be inspected separately. I mean, obviously, if it fits over the pins, you know the holes are generally, you know, within tolerance in terms of the MMC. You know, you would know that just by fitting on the pins, but you would have to inspect those holes to make sure that they don't exceed the upper tolerance limits. So the gauge only verifies positional tolerance has not been exceeded. It doesn't check the hole size. Okay, so here's another type of functional gauge. This one, we're gauging a primary datum as referenced at a maximum material boundary. Okay, so in this particular part, here's how the geometrics are drawn. In the orthographic views, we have a cylindrical datum here, datum A. That sticks up through. We had datum B is the surface right here. We have 3 holes. These 3 holes are are specified at MMC, okay, which is good. That opens us up to a functional gauge, and the datum A is at MMC as well. And then we also have C. We need the datum C to square up the part here. So how would the functional gauge be built? Okay, so what we'd have here is this is our functional gauge. We have a simulator for datum B, which is just this surface here, because datum B is a surface. That's our simulator for that surface. And then we have a simulator for datum A. Okay. Now, if we notice, datum A here is specified at maximum material boundary. Okay, so maximum material boundary for datum A. Okay, in which case, the simulator for datum A is made at the virtual condition. Okay, 500 thousandths is the maximum material condition of the shaft, and then what we're going to do to it is add, since it's an external feature, we're going to add to 3 thousandths. So this gives us a primary datum of 503. That's the virtual condition. Okay, and then now we have these pins here. These pins are made at 210, which would be this 219 minus 1, which is 218, minus the 8,000ths true position at MMC. So that's how we check this part. We're picking up datum C simulator, so when we put the part in, we have to clear the MMC of the shaft here, and then we also have to clear the MMC, the virtual condition of these 3 pins, and we also have to control the location of this datum C surface. Okay, I'd like to stop this movie here, and we'll continue with this topic in the next movie. Thank you.